Before we get started with the lecture, there's one thing I wanted to mention. During this lecture, I will be using some demonstrations that use sound to illustrate some of the concepts that we're talking about. I wanted to apologize for our viewers with different hearing abilities that it might be difficult for you to get the benefit out of some of those demonstrations if it's difficult for you to hear them. I should have said something while I was giving the lecture, so I wanted to apologize for not saying something at the time, but I do hope that for those viewers that have different hearing abilities, I hope that my explanations help you understand what's going on, even if it's not possible for you to hear what I'm demonstrating. Hello everyone, and welcome back. Last time we were looking at waves, and we were looking at some different properties of waves, different kinds of waves, longitudinal and transverse waves, and we looked at how they moved through some kind of medium. What we're going to do now is continue with that. We're going to look at what happens when we have more than one wave. How do waves interact with each other? This brings us to our next section, section 16, superposition and standing waves. The first thing I'd like to do is to talk a little bit more quantitatively about the equations that describe the motions of waves. Let's imagine that we have, say, a medium, in this case, maybe a very light medium, like a piece of string or something like that, or we might have something a little bit more heavy, like a medium of a chain or something like that, and imagine that we've got some oscillations moving through the chain. Now, my question is, what kind of equation or equations will describe what this motion looks like? Let's imagine that at some time we've got some piece of the medium chain or string or whatever it is, and let's imagine that it's the equilibrium position we'll assume is some horizontal shape like this, and at some point we're looking at some section of the chain that, or the medium, that is, say, in some kind of straight line like this. Now, let's imagine that there's some tension in the chain, and that's going to affect how the waves move through the chain. But let's just imagine we're looking at a small section of it. So here's a little bit of this chain, and then it connects somehow over here and over here. But we're just going to look at this section here. Well, let's imagine that we've got some section that we're looking at, this point of the chain, maybe like one of these little beads on the chain, or just a small section of the medium, or something like that. Now, what kind of motion are we going to get? What equation of motion is going to describe what this thing does? Well, we can imagine that this little bit here has got some little mass, say m, and what forces are acting on it? Well, there'll be a tension from this side pulling up that way, a tension from this side pulling down that way. Now, we might need to take the weight of the piece into account, but let's imagine, just for the time being, that the tensions in the medium itself are much, much larger than the weight acting on the little bit pulling it down, so we'll just ignore the gravitational forces acting on it at the moment. Well, if this is straight, then whatever force is up here will be exactly in the opposite direction as the force down here, and the net force will be zero. So we would expect there to be no acceleration of the object. Well, what would give us an acceleration? We would get an acceleration if these forces were not opposite each other. In other words, if we had some kind of a different direction, maybe like that on one side. In other words, if we had some kind of curvature for the wave. So if we have a straight section of the wave, that's not going to give us a net acceleration. What we need is some kind of curvature of the wave. In other words, if we're looking at this, say, as a function of position this way, if this is the x direction and we're looking at the displacement of the chain from the equilibrium, then we need some kind of not first derivative of the height, but we need a second derivative. We need some kind of curvature for the wave. Well, that leads us to a very interesting conclusion, that the description of the equation for the wave, the acceleration of the little point on the wave, is going to be related to the curvature of the wave. Okay, well, let's kind of write this out. Let's kind of define some parameters that we'll use to describe the wave and see what that leads us to. Let's imagine that this is our medium, so this is our object that's oscillating. So we've got this up here. Here's our medium through which the waves are traveling. And we're going to describe the position, the horizontal position, in terms of the x variable. So we've got some origin, and we'll measure the position along the wave in the x direction in this direction with the x variable. The displacement that the wave has from equilibrium. Now here I'm kind of making the assumption that we're talking about a transverse wave that's moving perpendicular to the direction of motion of the velocity, but really this would apply to any kind of wave in a much more general fashion. But we'll just assume we're kind of looking at a physical transverse wave like a chain or string or something like that. All right, so the displacement of the chain at some point we'll describe with the y-axis, so y is perpendicular. Now we notice that the displacement y depends on where we are along the x-axis. So y, we can see, is going to be a function of x. So different heights for the chain, for the medium, at different positions of x along the x-axis. But we expect the wave to be moving, so this is going to be going up and down. So not only is y going to be a function of x, but it's also going to be a function of time. So y is not only dependent just on x, but it also depends on time. It's going to depend on both of these variables. Now, what kind of equation of motion, or what kind of physical properties are going to affect the position or the motion of this little bit of chain? Well, what we saw was that the acceleration of this is going to be dependent on not the position y, but the curvature of the chain at that point. Now, what's the curvature of the chain? Well, that's how it curves in how y varies as we vary along x. So we're looking at a second derivative of y with respect to x. So d squared y dx squared. That quantity is then going to be related to the acceleration of this point. And the acceleration, we mean, how is this point going up and down? So we're talking about the second derivative of y with respect to time. So we're talking about d squared y dt squared. So we've got two second derivatives of y. One in terms of the position x, one in terms of the position t. Now, how do we deal with that when y is dependent on x and t, and we're trying to take these second derivatives? Well, we're going to take a different kind of derivative. We're going to take what's called a partial derivative. A partial derivative means that when you differentiate y with respect to x, don't worry about what t is doing. Just differentiate y like t was a constant, and when you're differentiating y with respect to x, just imagine like t is a constant and differentiate y with respect to x just like you would any other function, and just imagine that whatever t is, it has a constant value. And then and the way we write that is with not a regular looking d, but with kind of a funny looking d that looks like that. So this is a partial derivative of y, partial squared of y with respect to x. And then when we differentiate with respect to t, we're going to do the kind of the opposite. We're going to assume that x has a constant value in that case. So we're looking at just the acceleration of y at a constant value of x. And so we're going to take a partial derivative of y with respect to t. And so we're going to write it like this: d squared y dt squared. So we're going to be taking partial derivatives. So how are these two things related to each other? How does the curvature affect the acceleration? Well, I'll give you a couple qualitative ideas, and then I'll just put the answer down and we'll kind of just guess a solution. I'll just give you a solution, but we'll check the solution with our equation to make sure it works. So let's imagine we've got our medium here. Now, if we have a very light medium, a light medium can move very, very quickly. It's very easy to move a light medium, so we would expect large accelerations. A heavier medium is harder to move. You need greater forces to move it. So a heavier medium, or a heavier mass per length, we would expect to move the waves to move more slowly. On the other hand, I'll just do it with this one. If we have a very small tension, so if we imagine that this is very loose, then waves will move slowly because we'll have less force. But if I pull this very tight, then we would expect the waves to move more rapidly because there's more force. So the speed of the waves we expect to be dependent on the mass per unit length of the medium and also the tension that's in the medium. Okay, so given that, what kind of equation do we have that will describe this motion? Well, let me put that up. We'll take a look at it. What we find is actually a very, very simple equation, as long as you think partial derivatives are simple. What we find is that d squared y dx squared partial equals 1 over v squared, the velocity of the wave, times d squared y dt squared, the partial of y dt, second derivative. A general solution to this looks something like this. A function of y of x and t is equal to, now I said a general solution, this is not exactly true. This is a general harmonic solution, a solution of a sine wave that looks kind of like a sine wave. But what we'll do is we'll stick this equation in there and see what conditions we have. But this is looking basically at only a solution that looks like a simple harmonic motion solution, kind of like we did with the simple harmonic oscillator. So what I want to do is take this solution, stick it in here, and verify that this actually solves this result and creates an equality for the partial derivatives. Okay, let's do that. I'm going to erase some of this and we'll do that. So, starting out with our solution, y of x of t equals a sine kx minus omega t plus delta. We differentiate with respect to x, so partial derivative with respect to x. Derivative of sine goes to cosine, then we differentiate the argument, but assuming that x is the only variable, that brings out a factor of k. So we have dy dx is k, a cos kx minus omega t plus delta. Then differentiating this once more by x, we have d squared y dx squared equals, brings out another factor of k, but derivative of cosine is negative sine, so we have negative k squared a sine kx minus omega t plus delta. And then what's the derivative coming back up here? Differentiating with respect to t. Differentiating sine, we get cosine again, but differentiating the interior brings out a factor of minus omega, so we have minus omega a cos kx minus omega t plus delta. And then differentiating this one with respect to t, again brings out another factor of minus omega. Minus omega times minus omega is omega squared, but derivative of cosine is negative sine, so we end up with a negative omega squared a sine kx minus omega t plus delta. What do we want? We want d squared y dx squared, we want this to be equal to 1 over v squared times this. So I'm going to write this times v squared, and we will see, does that equal this thing? So, does this equal 1 over v squared times this? So this will be minus omega squared over v squared a sine kx minus omega t plus delta. And I hope that's all in the screen there. So, do these two things equal each other? Well, we've got a sine kx omega t plus delta, sine kx minus omega t plus delta. So let's divide that off. Now, this no longer equals this d squared term here. Dividing off the sine term, divide off the sine. We've got a factor of a, which is an arbitrary constant, factors off a, that works. We've got a negative sign, we've got a negative sign. So as long as k squared equals omega squared over v squared, in other words, as long as, let's multiply by v divided by k, v squared equals omega over k squared, as long as that is true, then this will be a solution to this equation. We could take the square root and we'll have v is equal to plus or minus omega over k. So we could have a positive or negative omega, and we'll look and see what that means. But basically, as long as omega over k is equal to the velocity of the wave, then that will be a solution of our equation. Okay, well, great. I'm going to come back to this. We're going to look at some other possible solutions to our equation. But let's just think about what this means just for a second.